Good afternoon, everyone. My name is Mo, and I'll be presenting our deployed systems paper entitled Change Management in Physical Network Lifecycle Automation, which is quite the mouthful. The paper talks about our experiences at Google to support network change management at scale over the last few years. Obviously, this is joint work with many of my colleagues at Google across dozens of teams. I'm presenting on their behalf. I'll preface this talk by saying that the scope of this work is Google's SDN-based data center and WAN networks called Jupyter and B4 respectively, though the systems in this talk are equally applicable to non-SDN networks. As you can imagine, Google's networks are vast and span the globe. This is a picture showing Google's cloud presence around the world. And this is a picture of one of our data centers in Finland. Each building has dozens of machine rack rows, all interconnected by thousands of networking switches, fibers, patch panels, and so on. It takes an army of technicians and engineers to operate one of these. And Google operates dozens of these data centers around the world. Now, the Jupyter and B4 network architectures have been in production at Google for over 10 years now. And in that time, we've faced many challenges. I'll list a few. The first challenge we faced is around scale. The scale of Google's data center and WAN networks is huge and growing rapidly. The more human touchpoints you have, the more intractable network management becomes. These networks are constantly evolving and growing in terms of capacity, number of sites, the technology used, and so on. Now you might ask, does this paper only apply to large networks? As you'll see, the lessons and tools of this paper are equally applicable to smaller networks. In fact, we use them to manage POP locations in smaller data centers too. The next challenge is around safety. These networks are in perpetual state of change for augments, migrations, expansions, and so on. The adage of the network won't break if we don't touch it won't work here. We need to support change happening multiple times a day across the world, especially since these networks are actively serving fabrics. We need to find a safe way to manage and grow them that's invisible to the network applications and running clients, and without network disruptions. The next challenge is around deployment. As you saw, this is a global operation. The deployment of a network fabric is a complex process that can take weeks or months and involves answering quite complex logistics questions like, how do you manage things like supply chain, material delays, project dependencies, and unpredictable capacity growth, and so on, all while maintaining standard SLOs for predictable end-to-end deployment times. Basically, how do you deploy networks efficiently and quickly? And finally, the question around interoperability. There are dozens of teams and systems that interact with the network, from capacity planning and forecasts, to detailed design, to materials ordering, physical layout, systems like SDN controllers, to operations and tools like installation, qualification, drains, repairs, and so on. How do you get all of these systems to effectively communicate with each other? And how do they have an authoritative, consistent view of intended and discovered topology? Before I go into the meat of the paper, let me briefly introduce some useful context on MALT. MALT is a language to model network topology at multiple levels of abstraction. For example, 1, we have models reflecting the high-level abstracted view of the network and the capacities between them. 2, models at the fabric building block level. And 3, models showing low-level details like specific racks, switches, their ports, and so on. A MALT model is essentially an entity relationship graph. Entities are like nouns. They can represent topology, for example, which 2 ports are connected, and taxonomy, for example, the hardware type of a given switch, and state, For example, a link may be enabled or not yet in service and undergoing link qualification. Relationships are like verbs. For example, a rack may contain a switch, or a trunk port may aggregate a few singleton ports, and so on. These models are versioned, immutable, and sharded. A consistent collection of models for a given snapshot in time is called a model set. These models reflect intended network topology. Online control systems, like our SDN controllers, stitch these intended views with discovered real-time reality and alert if any mismatches are seen. These models are stored in a replicated service called Malt Shop, and more details on this can be found in the NSDI 2020 paper on Malt. Example models are available for download and inspection at GitHub. The link is in the paper. I encourage you to check them out. Malt proved immensely useful at Google and is the foundational layer for our global network operations and services. We use it as the basis for SDN controller and device config generation, telemetry and network management tooling, for example, drain, qualification, installs, health monitoring, repairs, materials procurement for things like fiber bundles, optics, and so on, and port wiring instructions to data center technicians, and many, many more. It's essentially the lingua franca for network management. And as such, the content of this talk is more focused on how we generate and manage these models. Next, let me walk you through 4 of our model generation and management systems. And then I'll talk about some case studies of how these systems helped with the challenges I described earlier. First, the model design service is the front end for capacity delivery workflows to mutate current and future network models. It's essentially the right pipeline. It maintains a unified intent model, a high-level planning view of the world at a given point in time. This model contains an intent entity for each of our fabrics and interconnects between them. Now, an intent for a given fabric is basically a set of declarative design instructions. For example, for a given B4 neighborhood, it says how many blocks to create, which buildings this neighborhood should be created in, which technology to use, which prefixes to assign IP addresses from, and so on. A workflow may say, add a network of this kind at this time, at this location, with these properties, and the service would generate an intent delta and builds that change. I'll describe how in a second. The design service also provides a synchronization point, both for workflows to not step on each other's toes while making mutations to the same part of the network, and also by maintaining a common record of resource reservations, so that, for example, ports would not be double allocated. Next, the model build service. This is essentially a Malt-focused distributed data flow graph execution engine. The goal of this engine is to translate or compile high-level intent into detailed models. This is where all network design decisions are made about port allocation, link striping, IP address allocation, and so on. This is also where we do many of our network invariant checks and validations. For example, checking that we don't exceed a hardware table size limit for a given chipset, or assign duplicate IP addresses, and so on. The service operates on 1, data, which are the edges of the graph, and mostly in the Malt format. And 2, rules. These are the vertices of the graph. These are basically domain-specific model generator building blocks called build units. This service has 2 important properties. 1, its execution graph is input dependent. When given an intent model, a special pre-processing step would compute the graph, and then the service orchestrates the distributed model computation. And 2, The system is stateful across subsequent builds, since we have to honor previously made decisions about port allocation and the like. This is critical for build stability and operational safety. Since only a small subset of the intent model would typically change at any one time, this engine makes extensive use of caching to short-circuit previously done rule executions. It's not unusual to see cache hit rates in the high 90s. Next, we built a model query service. As our understanding of the network grows and we introduce new technologies and concepts into the fleet, we needed a way to evolve how we model things in Malt. To do that, we designed the build service in a way that it would simultaneously generate semantically equivalent models in different profiles every time we generate a model set. In this example, originally we modeled 2 ports directly connected to each other, but then in a subsequent profile, we decided it would be better to represent the bidirectional links between them explicitly. To make life easier for model clients, we built a model query service, which is the recommended read API for models. So for example, a client may ask, what is the set of enabled interfaces on switch X? Or what are the BGP peers of fabric Y at time T? These semantic and canned queries provide a stable API to clients. This serves multiple purposes. They allowed profiles to evolve, all while insulating the clients from needing to care about how things are represented or how that changes. Next, we built TopoPlan, which, as the name suggests, is a service to manage future network topology. This is analogous to a software version control system and supports similar APIs to create branches, commits, rebasing, promoting a change, and so on. So we have the concept of a plan. This is similar to a commit branch. We maintain a master plan of record plan, which contains a sequence of changes that are committed, meaning that we have financially committed to these. For example, material orders have already been placed. These are changes that are typically very hard to reverse. Network planners may create arbitrary side plans and what-ifs for provisional evaluation and analysis. And these may be committed to the POR in some cases. Next, we have the concept of a plan point. This is similar to a code commit. It's essentially an intent delta over the unified intent model. A project like a fabric migration may contain an arbitrary number of plan points, which represent the set of mutations for all intermediate network states for that project. The build service can evaluate and generate detailed models at any point at any branch. This is invaluable because, 1, it allows us to create network designs for the future, enabling most of the pre-deployment preparation steps, like fiber length computations and material orders, to take place. And 2, it allows us to detect potential issues weeks or months prior to actual deployment. For example, double allocating a port for 2 different augments, or an invalid execution sequence, and so on. And 3, it allows us to break down large, complex processes like live fabric migrations into smaller changes that are more aligned with smaller failure domains, and that can be rolled out gradually without putting the entire live serving fabric at risk. Now, in the case of unforeseen operational issues, we also have support to return to known good state, which in some cases might require us to unwind several stacked changes. Thankfully, we rarely use this in practice. Now, with those 4 capabilities in mind, let me give you some concrete examples on how these improved our overall deployment times and project concurrency. First is a case study we call dead zone reduction. Deployment projects, for example, things like new network deployments, expansions, capacity augments, and so on, are very long-lived, meaning they can span weeks or months from start to finish. This is especially true for projects requiring construction work, obtaining permits, long lead times for materials procurement, and so on. Prior to the improvements discussed in this paper, these projects were effectively serialized, meaning that no part of Project B may begin until Project A is fully completed and that capacity is turned up. This is in part because the model basis for the design of Project B depended on Project A's view being visible at head. Our old network modeling system didn't support planning and effectively had a maximum stack depth of 1. In reality, some of the prep work for Project B should not be blocked on A's completion, especially things with long lead times like material orders. In essence, if you have a committed execution sequence, you should be able to front load most of the prep work. The detailed planning capabilities of TopoPlan essentially allowed us to decouple future network state from the current live models we use to operate the serving network, and essentially allows arbitrary stacking and pipelining of future projects. In practice, the capabilities effectively streamline the execution of our deployments, saving us weeks or months at our data centers. Let me describe another case study, WAN change management. Most of the change at a data center fabric happens within the data center itself, so that deployment projects in multiple data centers can more or less operate independently of each other. Our WAN, on the other hand, is a globally connected network, and these projects are often interdependent, and with planning support can form long dependency chains. For example, if a network in Taipei is port constrained, a capacity augment between networks in Singapore and Taipei might require some capacity to be decommed between Taipei and Oregon first. This dependency can be expressed explicitly. The emergent structure of TopoPlan plans made it clear what projects depended on what, and what the impact of a change would be, in a way that was not clear to humans before. Due to unforeseeable real-world constraints like supply chain disruptions, construction delays, and so on, the actual execution sequence of these projects almost never matches the global order in which they are created at quarter boundaries. TopoPlan allowed us to be flexible and resilient to these factors by exposing actual dependencies, allowing project execution reordering where possible, and also allowing concurrent project execution if no such dependencies exist. Now this brings us back to the challenges I described earlier. To conclude, we address scale by automation as much as possible. The more human touchpoints you have in your planning and deployment pipeline, the more likely you are to introduce costly errors. Having automated network design takes humans out of the loop and allows for sublinear team growth with respect to network scale. We address safety by breaking down large, complex processes into staged, gradual changes aligned with smaller failure domains, as well as validating network invariants like scaling limits or duplicate IPs as early as possible. We address deployment efficiency by having support for detailed future planning and enabling flexible planning concurrency, branch management, and dependency tracking, as well as having an integrated supply chain. This streamlines our deployments and enables a more predictable SLO for our projects. We address interoperability by having a common modeling language with a consistent, authoritative view of network topology at any given point in time, and providing both stable read APIs and agile profile evolution. Thank you all very much. I'm happy to take questions.
Okay.